Last meeting, we have talked about vector space, subspace, spanning sets, and linear independence. Today, we are going to discuss about the basis. The definition of the basis is that a basis of a vector space V is a set of vectors V which is equal to the set of vectors V1 to Vn, such that that set of vectors spans V, and also that set of vectors are linearly independent. So last meeting again, we'll talk about how to identify if a vector spans vector space and how to determine linearly independent vectors. Now we have a note for this discussion. Suppose we are given a set of vectors as a vector V is in span S if and only if V is a linear combination of the vectors in S. That is, the vector V can be expressed as a linear combination of this set of vectors. Okay, the vector V, so meaning this V, exists if the determinant of the augmented matrix mean here is the augmented matrix of augmented vectors, adding V1 to Vn. Kung ano to yung determinant niya, it would result to a non-zero value. Meaning if your determinant of the augmented matrix is not equal to 0, therefore the vector V exists, or this vector V exists. If this V exists, then V is in span S. So meaning this V belongs to this set of vectors. If upon getting the determinant, it resulted to a 0 value, meaning that V does not exist. Okay. This is for identification of span. Say, for example, you are given these vectors V1, V2, and V3. So you want to determine if this set of vectors is a basis of R3. Again, to identify if this is here, we must, of course, show that this set of vectors spans the vector space R3. So meaning your span V1, V2, V3 is in R3. Also, we will show that that vector, a given vector, is linearly independent. We have set of vector V1, V2, and V3 is linearly independent. Again, to determine if this set of vectors spans R3, we must show that the determinant is not equal to 0, just what I have mentioned earlier in our note. So for this span, say we have vector V, composed of x, y, z, which is in our R3, we want to show that the vector v exists. Okay. What we're going to do is we will get the determinant of the augmented matrix. You're going to augment v1, v2, and v3. Yun ni itsura. You have 1, 0, 0, 0, 1, 0, 0, 0, 1. To get the determinant of this, suppose we will call this matrix A. So getting the determinant for our matrix A, that would be, since diagonal, we have diagonal entries only, that would be 1 times 1 times 1. So this is equal to 1. So you can see equal to 1 is not equal to 0. Therefore, this V exists is in R3 and S spans our vector space V. Okay, so the first property satisfied. Moving forward to our next second property for showing that the vectors are linearly independent. During our discussion linearly independent, we must show that this vector, the what you call that one, linear combination of this vector is equal to 0. We want to show that the values of our coefficients is equal to 0. So for linear independence, we have A1 V1 plus A2 V2 plus A3 V3 is equal to the 0 vector. Substituting the value of our V1, V2, and V3, zero, zero, zero. Now, distribute A1, so we have A1, 0, 0, plus A2, 0, 0, plus A3, distribute A, it should be what? Yes. Erase. Okay. This should be 0, A2, we have 0, 0, A3 equal to 0. If we're going to transform this into a system of linear equations, it would look like this. We have A1 equals 0, A2 equals 0, A3 equals 0. So you can see your A1 is equal to A2 is equal to A3. What does this mean? So therefore, mapakita na to that the values of your E's here, AI's here is equal to 0. Therefore, the vectors are linearly independent. So we have P1, P2, P3 is linearly independent. So you can see linearly independent siya as well as the vector spans are R3. Therefore, we can say that the set S is equal to V1 into V2 is basis of R3. Okay, see that. Understand? Actually, this identity matrix here, if we are going to augment this T matrix, this is the standard basis for R3. We encounter this. This is already, no need to solve, but this is already standard basis for R3. Okay, so next, let's take a look at another example. Suppose we have these vectors. Now, by the way, this computation here, okay, so we only use a determinant. Actually, there is a long computation for this. Now, looking at the determinant, we already know that this is a basis. Actually, if you can still remember, knowing linearly independent, if we solve for the determinant, if it is not equal to 0, we already know that it's linearly independent. Okay, no need to do this. We just look at the determinant niya. If you check the determinant is not equal to 0, automatic it spans V, the vector space V, and as well as it is a linearly independent vectors. Okay, so in here we use the long computation for determining it linearly independent. Here long the short computation utilizing the determinant. Okay, for example, here given vectors v1, v3, determine if the set v1 set as v1, v2 of vector is a basis for R2. So again, we must show that the vectors 1, 2 spans V or spans R2. And also we want to show that this vector is these vectors, this set of vectors is linearly independent. So first, if we are going to do long computation for this size span, in here, we must introduce, this is for long computation, for span, finding the span, or long computation, for here, the set of vectors, um, vectors spans are okay. So in here, we must introduce we have x, y that belongs to R2. Okay, we want to show that this x, y exists, right? So to determine that, we are going to do the linear combination plus V2. V2, this is equal to this xy here. Okay. This is our new vectors. This is V. And so we can use being So this is B. So we have A1. We have 1, 0 plus A2, 1, 1. V is XY. And then distribute. We have A1, 0 plus A2, A2. This is equal to XY. Okay. Now, we are going to transform this into a system derivation. So this will become A1 plus A2, which is X. We have A2 is equal to Y. Okay. Now, as you can see, we already have a value of our A2, which is equal to Y. So therefore, we can substitute this value of A2 to here. So we have A1 subs 2 equal Y in equation 1. So we have A1 plus Y equals X. So A1, we find value of A1, this is X minus Y. So as you can see, natin values atong A1 and A2. Therefore, this um, this vector exists. Okay, so therefore, we set S spans R2. Okay, checking first. For the second, if linearly independent, utilizing the computation again, we are going to use this linear combination again. However, we're gonna equate that to 0. So we have 1, 0, 8, 1, 1. This is equal to the 0. And then distribute A1, 0 plus A2, A2. This is equal to 0, 0. We are now have two equations, two unknowns. We have A2, 0. We have A2 equals 0. As you can see, we already have a value for our A2, which is equal to 0. Now we want to show that your A1 is equal to 0 also. So we will plug in the value of A2 here in our first equation. So we have A1 is equal to 0. A1 plus 0 is equal to 0. So your A1 is equal to 0. So as you can see, napakita na to siya na your A1 and A2 is equal to 0. Therefore, the set S, which is equal to V1, V2 is linearly independent. Dependent. Therefore, we can say that the set S is a basis of R2 alone. Understand that. Right. Now, for this example, I'd like you to do this on your own. I want you to submit the result of this example next meeting. And then together we will answer this if this is a basis or not. All right. And this one also. Okay. Para ma-practice mo. Right. Now, for computation, I'd like you to practice in here, you can do mix. Okay. You can do isa finding the determinant, isa long computation. Okay. The same ani. Isa finding the determinant, pwede ka long computation on the other. Right? Next is the dimension. The dimension of a vector space V is the number of vectors in a basis. So we write dim V for dimension. So in example, if we have this Rn, now if we're going to find the dimension of Rn, we're just going to look at this superscript here. So for the dimension of Rn, we have n. For the dimension of 2 by 2, we have 2 times 2 is 4. This means that, I think the dimension means the total number of elements inside your vector. Okay, so as you can see, for 2 by 2, we have 2 times 2 equals 4. For the R3, the dimension of R3 is 3. All right. So I think that's all for this topic. Thank you so much for viewing